Hey guys, this is going to be a short video for the final exam preparation. Due to a curious thing, the online course is different in material than the actual brick and mortar ITT courses, but through some regulation, all the exams have to be the same. As a result, there are some things that haven't been covered, so there are new topics only on the final exam, for which I apologize. So I'm going to do my best to give you guys sort of a crash course in those things to make it so you shouldn't have too hard of a time getting a good grade on the exam. So for now, we're going to go over some of the things that we already covered in class, and then in either this video or the next, I will talk about the new topics. Alright, first thing is basically how adding up forces. So this is not, hopefully isn't new to you guys. Adding up forces. If you remember from assignment 1, I posted a video. You had to, find the resultants of these odd sets of forces and say it was, like this or something like that. There's none of that on the final. The questions are more about, adding up, up and down, finding the total sum of like up and down vectors. That's pretty straightforward. And some basic word problems on how you do more difficult problems. As a reminder for one of these, we're going to cover something called the polygon method of adding up forces. So imagine you had two steel walls, some distance apart. You hung a wire between them. You hung some weight, clamped some weight in the middle here, and hung some weight off this thing. 100 pounds or 100 kilograms. There is a force on this weight due to gravity. There's a force due to this rope. There's a force due to this rope. That's actually in line with the rope. And if you wanted to find out what they were, you could do it with the polygon method. So, draw your little axis on your mass. Find the angles to these ropes. We'll call that phi1, measured from the positive x-axis. Call this one phi2. Again, measured from the positive x-axis. And then we'll simplify this to just the x and y diagram here. And the goal is to find out what's the force F1 in this rope and F2 in the other rope. That's the goal here. If we look at the force due to gravity, we know what that is. That's down with 100 kilograms times g of force. If you remember how we added forces before, we saw that we could basically put forces tip to tail together in perpetuity, and whatever their sort of total thing was, this big vector here, this was the addition of those vectors. And we're basically playing off on this trick. So if you look at adding F1 to this, you go tip to tail, this is going to be at phi1 here. If you look at F2, it's going to come off this thing somewhere at an angle of phi2 from the positive x-axis. It's going to be on some dotted line like this. And F1 will be this little vector here, and then F2 will be this vector. If you do everything right, you'll always get a little polygon like this, and that's why it's called the polygon method. So if you have something in static equilibrium, some box of some kind with some huge number of forces on it, pulling it, say it's attached to a lot of ropes. If you go in the XY axis and you just add them all up in a reasonable way, you will invariably get a polygon, where if you keep going tip to tail with all these forces, you'll eventually end up at 0. That's the polygon method. I didn't go through any of the numbers because we don't need them for the final. I'm trying to keep it short. So that's the polygon method. Next, we're going to go over some moment balance stuff again. So we've talked about how the sum of the forces in this course is always equal to 0. We also learned that the sum of the moments is always equal to 0. There are a few questions in the final about this that ask you to go through numerics for this part. So I'll go over something similar to one of the ones on the final. Let's say you had a ladder leaning up against a wall. Let's see, there's some force on the ladder due to the ground. We'll call this F1. Call this F2. Basically, there's some force on the ground sideways, there's some force from the ground going up. There's some force from the wall going this way. We'll assume that there's a wheel here, something like that. So there's only force pointing to the left from the wall. There's nothing up or down right here. And there's a few forces here on the ladder, 2 people. So this guy 200 pounds. Call this guy 100 pounds. I'm going to add some dimensions. 5 feet. Call this 6 feet. And call this 4 feet. We'll say that this is 14 feet. Notice that I didn't note down any of the angles here, and that the way I've drawn it, this is the stupidest ladder ever. That's because it doesn't actually matter the way we're going to do the problem. If I wanted to know what this force is, force due to the wall right here, we could find that out using sum of moments equals to 0. It's logical to take the moments about this point, A, because we have these unknown forces F1 and F2 passing through A. And so if we take the moments about here, these things get multiplied by 0, and we don't care about them at all. Sum of the moments about A equals 0. So this equals minus 100 pounds times 5 feet. Notice that this is the line of action of this 100 pounds, is this vertical line of here, this dotted line, and that is 5 feet away from A. And you keep going here. This distance from here to here is 5 feet, and that's what matters. If you wanted to, you could find the distance from this point to this point, and then find the sine of this angle, and then you'd have this force times this distance times the sine of this angle, but that just makes more work. If you look at the distance between the line of action, just this dotted line here, and the point you're taking the moments about, that's what really matters. Yeah, it all ends up being the same. So it's 100 pounds times this 5 feet. Likewise for this one, minus, in this case it's 11 feet between the line of action of this force and A, times 200. Notice these are negative because they're rotating in the negative direction. And then we add up FW. So plus, since it's right-hand rule, thumb goes up, fingers point in the direction of positive rotation. positive moment from FW, so that's plus 14 feet times force of the wall. This all equals to 0. So now we can solve this to find FW. Got a handy calculator. Force of the wall equals 192.86 pounds. This is very similar to one of the problems you're going to see in the final exam. The key here to remember is it's all about this line of action business. So you look at the way the force is acting on this line of action, and you look at the distance that that line is from the point you're taking the moments about. It's all about that. So that's how you solve that. There's a similar problem on the final exam. Alright, I'm going to break this video up now and move on to the next topic.